Hello. Today we're going to talk about programming concepts. Now, before we get into this presentation, I want you to stop for a moment, look around, and try to figure out how many computers do you have around you. Go ahead and pause the video for a moment if you want. Ready to go? Well, I'm hoping you said at least one because I can't see how you would be watching this without a computer. But did you include your monitor or monitors? Did you include your phone? Do you have earbuds around? And just looking around at my specific office, I have my main desktop. So there's one. I have two monitors. We're up to three. I have a drawing pad. So there's four. I have my earbud case with me. So the case itself has a small computer in it to handle the charging. So I'm up to five. And then each earbud's going to have a miniature computer in it to handle the Bluetooth communication and audio decompression and translation. So now we're up to seven. I have my printer with me, so we're up to eight. And I could probably keep going. When we talk about programming computers, we're talking about more than just desktops. There are computers that surround us everywhere in this day and age. And that is something you want to keep in mind. When we're talking about computing, and specifically when you're talking about the potential of a career in programming, that encompasses a lot of different areas. Now, for this course, naturally, we're sticking to programming personal computers. There's no way that I would throw first-time programmers into the pit of despair that is embedded device programming, or say writing a program to control the TV remote. I'm not going to do that to you. That wouldn't be nice. But do keep that in the back of your head as we go through this course and as you listen to this presentation, that when we talk about programming, we are talking about more than just doing what we typically think of as a computer or a personal computer. So, what is a computer? If we go with this nice little internet definition, a computer is a machine that can store and process information. Most computers rely on a binary system, which uses two variables, 0 and 1, to complete tasks such as storing data, calculating algorithms, and displaying information. Oh, that was helpful. But seriously, a computer is, to put it reductively, a device that helps us in computing. Got a couple of images here of ancient computers, which is closer to what we would in the modern day understand as a computer. You know, they used to be the size of rooms with like physical switches and fuses everywhere. You had to be as much mechanical engineer as electrical engineer to be able to operate and maintain the things. And if we go further back in history, I mean, an abacus is generally considered to be the world's first computer. It does computing. They're not easy to learn and master, but if you learn and master the use of an abacus, you can do some pretty complicated calculations and equations pretty fast. I mean, they're not a slouch when it comes to doing mathematics. There's a reason why the ancients used these, and it wasn't because they were dumb. Now, so any device, technically speaking, that allows us to do computing or allows us to do calculations is a computer. Though, of course, in modern parlance, when we talk about computers, we're talking about the thing that's under our desk or on top of the desk, as the case may be. Now, I've already sort of hit on this a little bit, but there's a lot of different places in the world that we encounter computers. Your car, for example, unless you have a really old classic car, is going to have multiple computers in it, helping control all of the various systems. Computers are also very much used in industry. Now, if you're going through and sort of reviewing the slides on your own, you should be able to play this video from within here, but I think due to the security settings I have on my computer, it won't play from the slide. We'll just hop over to YouTube here real quick. And this video does not have sound, just to make that clear. And so the whole point behind this is it's a tomato sorting machine. You got tons of tomatoes, just hundreds of tomatoes per minute going down this machine. And the point is that there's going to be desirable tomatoes and undesirable tomatoes. So I skipped forward a little bit here, and if we watch the bar here, pretty soon there'll be a little tomato coming across. There it is. That's an undesirable tomato. Whap! And that little arm comes down and flicks it away. And as it continues, you'll see, I think, is that one? Nope. No, that one will get flicked. There we go. Yep. See, we get all sorts of flicks coming out now. This is done through computing. There is a computer controlling this. There is a camera that is looking at and analyzing the color of the tomatoes. And when it detects a tomato that it doesn't like, it causes these little lever arms to flick out and tap that tomato out of the path so it doesn't go with all the good ones. Perfect example of practical computing. Someone had to write this program. Someone had to write the code to control these servo motors here to flick little plastic arms out. That's programming. Of course, we can also find computing in weird and unusual places too. Now, if you do not recognize this, this is the game Minecraft. People with entirely too much free time on their hands have gone through and recreated CPU architecture complete with memory inside of Minecraft using redstone circuits. This is basically an exploded three-dimensional view of what your CPU and motherboard looks like, complete with the ability to do displays, and it has a little control pad down here that can be used. You can literally play Tetris inside of Minecraft that is being simulated on a properly architected CPU. Very much worth looking at if you've got any interest or desire to know, like, what does a CPU actually look like and how does it function? If you have Minecraft, to go and find one of these computer maps and download it to take a look, because they are incredible. And like I said, took entirely too much time. This over here is a Dwarf Fortress computer. I believe this is one of the ones, although I could be mistaken, that uses fluid dynamics as its computer system. It basically uses pressure from water levels, not shown here, as storage and memory cells in order to do the calculations. And it can do full-on multiplication, division, subtraction, addition, and correctly calculate out the answers. So you can find computing in very strange places and in very practical places. But, more formally, what do computers do? Like, what purpose do they serve in our world? Like, why should we care? Well, for one, they help us do calculations. Think for a moment about all of the complexities involved in, say, designing a drone. You want to take some aerial pictures of your neighborhood or your house or something like that. And, you want to design the fan blade of a drone. Well, how much lift is that one blade going to produce? How fast does it have to spin in order to produce the lift needed to lift the drone up? Can the materials take that stress? Now, if you search on YouTube, you can find videos where people have taken CDs or DVDs and spun them up past the maximum speed, and the material can't take the stress and it just disintegrates. It rips itself apart. You can do some pretty intensive calculations to figure out what that speed is based on the material. Computers can help us do that. They can help us store information. I have the entire collected works of H.P. Lovecraft in audio form on my phone. probably about 20 other different audiobooks. I've got the Silmarillion in ebook format, along with probably another 20, 30 different books, all stored on my phone. Now, and even more information than that can be stored on computers. Historical meteorological data. So we can try to do analysis on weather patterns to try to predict weather better. All of that's computers help us store that information. Automate boring tasks. We saw that with the tomatoes. Just think for a moment. How many people would it take to sort all those tomatoes? You'd have to pay like $50 a tomato based on the labor charges, right? To sort them that fast, to have enough people to sort tomatoes that fast, it wouldn't be practical. Or say you've got a huge pile of marbles for whatever reason that you need to have sorted by color. Computers can help us do that. Provide safety oversight. Think about a power plant, any type of power plant, nuclear, gas, coal, right? Doesn't matter. They're all horrifyingly dangerous places. You have got massive amounts of heat, massive amounts of pressure, and massive concentrations of electricity. That is not something you want to have something going wrong with, right? That would not be good regardless of the scenario. And so computers can help us provide safety oversight. Maybe a little bit less drastic example, most cars these days have lane guidance computers in them, where they will use IR sensors to try to detect where the lines are in the road. And if it detects that you're drifting, it'll beep at you. And of course, far more important than anything else that I have listed so far, computers help us feed our cats. I'm serious. This is absolutely critical to the continuance of society. My cat absolutely loves his automatic feeder, to the point where he actually begs me to turn it on, even when he's not hungry. Okay. Common words you'll hear. Now, people complain all the time about jargon. Why can't you just say what you mean, right? By the way, if you've never read any of XKCD's stuff, I can strongly recommend it. It is nerd humor at its finest. And he did this thing where he tried to describe a rocket, as he puts it, explained using only the 1,000 words people use the most often. Notice he can't say the word 1,000 because apparently 1,000 isn't in the top 1,000 words that people use. And so we have wonderfully descriptive passages such as, thing to help people escape really fast if there's a problem and everything is on fire so they decide not to go to space. Thing to control which direction the escaping people go. Stuff to burn to make the box with the people in it escape really fast. Place where fire comes out to help them escape. Yeah, it's silly, right? We can't describe a rocket like this. It doesn't work. You can't do it. And so this is why we have jargon. You have to have specialized terms to be able to concisely explain complex concepts so that way you can have a conversation that doesn't take 5 times as long as it should. And this is a list of some of the more common terms that you are going to be hearing me say throughout this course. Compiler, source code, executable, compile time, runtime, debugger, interpreted language, source control, bugs. These are all terms that you are going to be encountering over and over and over again. Let's start off with this chunk of 4 here. Source code, compiler, executable, interpreted language. Source code. As you may have already learned, or you will soon learn if you are taking the computer fundamentals class at the same time as this one, computers only understand zeros and ones, on or off. That's the binary language. That is the only language computers understand. When you run an executable, when you run a .exe file, that is a file that is in binary. It is a series of zeros and ones that provide instructions to the computer. We as humans can't write code like that. It's like if you just stare at a solid block of zeros and ones, our minds can't process stuff like that. There are obviously some exceptions, but they are by far exceptions. Even if you know what you're doing, trying to interpret binary is a phenomenally slow and painful process. In the computer game Rogue Trader, there is a section of the game where if you don't have a certain party member with you, you reach this door and all of the door codes, all of the dialogue options are in binary. What you're supposed to do is go find the correct NPC or find a translation gizmo to translate it, and then you can very easily do it. Me being the stubborn person I am, I was like, I know binary. I can translate this. It took me an hour to translate this very small little chunk of text. It was not worth it. I know what I'm doing, mostly. So yeah, humans, we can't write in binary. So instead, we've developed source code. Plain text, you can write it in Notepad. Like I've said before, please don't ever actually do that unless you have no choice. But it's just plain text. X equals 5, Z equals 7, or Y equals 7, Z equals X plus Y, print, the answer is Z, right? Plain text, we can read it, that is source code. Useless to a computer. So to make it useful to a computer, we take a compiler and run it through that. Now, I'm grossly simplifying the compiling process here. It is a process, it has multiple stages. If you continue on down the programming rabbit hole, you will get more detail about the compiling stage. I just want to point out that I have grossly simplified the compiler stage because for this class, the details do not matter. You take your source code, you compile it, and that process of compiling, of translating your source code into binary, once it's finished, will sometimes result in an executable. And that's why we have executable and interpreted language here. When you look at a file, when you run a file on your computer, chances are it's going to end in a .exe. It's an executable file. You've got a language like C, C++, C#, Fortran, Cobalt, things like that. When you compile it, the end product is going to be an executable that you then have to execute or run to actually have the program do something. However, some languages are interpreted languages. The compiling and execution of the code basically happens almost at the same time. You compile it and then immediately run it. There is no file produced that you can run later. This is what, say, JavaScript and Python does. On a web page, you can hit F12 to view the source of the web page, and depending on the page, if you dig around, you might be able to find the JavaScript that is running that page. It is still in its source code format, and it's not compiled and executed until you actually load that page. At that time, the code is compiled and then immediately executed. There is no executable file created. Same thing for Python. While you can create executables for Python, we are not going to in this class, but Python is designed to always remain in its source code format, and then when you run it, at that time, it is compiled and executed. So what language do you use, right? So you've got many different languages. As the list here goes, C, C++, Cobalt, Fortran, C#, F#, Boo. Yes, there's a language called Boo, and that fact immensely amuses me. Go, not the game. Java, JavaScript. Do not confuse those two. The programmers in each of those get really annoyed when you do that. Python, that's what we're using. Ruby, Basic, SQL, HTML, CSS. Yes, HTML and CSS are technically considered programming languages. They are interpreted. Swift, R, Rust, not the video game, and PHP. This is not by any means a be-all, end-all list of programming languages. There are more. So which one's the best? Well, none of them are the best. Let's watch a little bit of a video. We're not going to watch the whole video. I do strongly recommend that you go and watch this video on your own time, the whole video. It's really quite fascinating and educational. Now, if you just do a search for "improved my code by," you'll find this video. It's from Stand Up Maths, and well, we're not, like I said, we're not going to watch the whole thing, but I do want to watch just a little bit of it.
It's true. A viewer says one of you, I'm holding you all collectively responsible, took some terrible Python code of mine and made it over 4 million% better, which is to say it achieved the same thing but faster, specifically 408,322,778 times faster, which is a significant improvement. So here's what happened. In a previous stand-up maths video, I referred to an even more previous episode of the podcast, A Problem Squared, which is the podcast I do with Beck Hill, file photo currently not found. And in that podcast, someone had asked if I could find 5 words that each have 5 letters. It was Wordle inspired, but between them they have 25 distinct letters. So I wrote some terrible Python code, and it eventually, I say eventually, for a very strong definition of eventually, found 538 such lists of 5 words. And that's if you exclude anagrams. For example, here's one such list.
So again, just to make sure everyone understands what's going on here. So we've got 5 words, and none of the letters are repeated amongst these 5 words. This is the only D. This is the only G, so on and so forth. And going back to what can computers do for us, well, this is actually a perfect example of why we might want to use computers, right? We want to data mine something, and yes, we can do it manually, but the amount of time and effort it would take to do this manually would be very high and very error prone. Humans don't like doing dull, repetitive tasks very much.
5 words, 5 letters each, 25 distinct letters with 1 letter left over, because there are 26 letters in the standard English alphabet. And when I wrote the code, I realized it was not the optimal code. In fact, it took about 32 days of runtime, specifically 2,760,670.3 seconds, known colloquially as about a month. Just over a month.
So yeah, this is, again, that might sound like a long time, but programs can be very fire and forget. And even if you have good codes, like this is not really that unusual to have a program that needs to run for a month. Like the big AI models that exist right now. Yeah, those can take literal months, like multiple months, to actually fully run a training cycle on the big data AI models. If you are trying to calculate meteorological simulations for weather patterns, these are huge, massive, lengthy calculations. Pixar movies, 3D animated full feature films. Games are measured in frames per second. Usually if you've got less than 60, you get made fun of. So, 60 times per second, as you're drawing a new picture. 3D animated films are typically measured in minutes per frame. Like, it can take 5 to 10 minutes to generate a single frame of the movie. It can take months to fully render Shrek, for example. When you think about all the lighting calculations that need to be done per frame for a 4K video. So, massively long calculations like this aren't necessarily a sign of bad code.
So, the rough timeline of what happened, there was the day I recorded the podcast, had a lot of fun, talked to Beck about the problem and the solution, enjoyed it so much, I thought this would be a good video. The very next day, I filmed that video. Videos, however, take longer to edit than podcasts. So the podcast came out first on what we're now going to refer to as day 0. Because on day 1, an individual named Benjamin Passen had already beaten the time my code took. So my code took 32 days. Benjamin was able to do it in 15 minutes, which was so hilariously faster. I was like, oh, I'm going to have to add this into the video. And
So again, we've got, same language. He wrote his code in Python. This Benjamin individual wrote their code in Python. So we're in the same language, and already we've gone from 32 days to 15 minutes. And the reason why I want to stress this, and part of the reason why I want to show this video, is to stress that badly written code is badly written code. It doesn't matter the language. Badly written C++ code is going to run slower than well-written Python code, or even well-written JavaScript code. JavaScript is routinely mocked for being a very slow language, but as long as it's written well and isn't trying to do something out of its wheelhouse, like, say, fluid dynamic simulations, it's going to work just fine.
Sat down, I was actually in Greece at the time, sat down in the hotel room, filmed a little update of me running Benjamin's code, put that in the video. And actually during that time, someone else, Neil Coffey, they got it down to 15 seconds. It's just ridiculous. So actually Benjamin and I...
Now we have a language change. Java is faster than Python. And because they were probably also well-written Java, we have gone from 32 days to 15 minutes to 15 seconds. We're not done.
Both coded it in Python. Neil stepped in using Java and got it down to 15 seconds. But that came so close to when the video was going out. Like, it was already edited. I think we'd uploaded it even. We weren't able to add that in. So we're like, that's fine. I'll make a note of that. We are cool. The video went out. And then all just chaos broke loose. Loads of people were now trying to find code that could find the same results but faster. And someone named, I'm going to get this wrong, I'm very sorry, Ilya Nikolevsky. I'll link to everyone's code below, by the way, if you want to check it out. They coded it up in C++ and got the time down to 5.86 seconds. Then Guy Weges, sorry about that, they just did it in regular old C. No pluses to be seen. They had 2.58 second runtime, and then we got right down to a second. So Kristen Paget, we'll go with that, also in C, 1.045 seconds. So almost as soon as the video was out, the time, which had been 32 days, down to 15 minutes, down to 15 seconds, was now in the 1 second category. And I'm skipping over a lot of other bits of code people sent in. These are just the highlight times that I happened to notice as it was all happening. Sure enough, we went below a second before too long. In Rust, there you are. Orson Peters, using Rust, one of the most hilarious of all the languages, got the time down to 0.48 seconds. We're talking...
So again, Rust is not known for its speed. Like, Rust has things that it does really well. I'm not familiar enough with the language to be able to expand on that statement. I just know that there are definitely uses for Rust, but generally speaking, in terms of raw processing speed, Rust cannot compete against C or C++, which we will see here in a moment, but still, well-written, well-structured Rust, half a second, compared to badly written Python, which took 32 days.
Half a second to do what took me a month. And then finally, the current record, although I have no doubt the moment I stop filming this, someone else will improve it.
Yep, and they did.
But at the time of recording, the record is held by Sylvester Hesp using C++, and they'd held the record previously, I think. They'd definitely written a lot of different versions of code. They currently have the record at 0.006761 seconds. So a lot.
So, in other words, 6.7, or if you want to round it, 6.8 milliseconds in C++. And the current reigning champion for this little competition is in C++. All right, so what's the point of this? Besides looking at that and going, what have I gotten myself into? It's like, at what point did that become silly to you, right? At what point did that become silly? Obviously, a month to answer the questions, not good, right? We would want to be able to generate that answer faster than a month. 15 minutes, that's still a reasonably long time to wait. 15 seconds to get that kind of an answer? I wait longer than that for Elden Ring to load. I mean, seriously. Now, that seems like a reasonable amount of time to answer this type of question. Sub 1 second? Okay, now we're just showing off. But it really just varies on what the user wants. How fast does the user need this answer? Like I said, 15 seconds, heck, even technically 15 minutes for this kind of an answer, that's fine. But if you're writing a program that's helping control the thrusters on a rocket that's going up into space, yeah, no, you probably need slightly better processing times than that. So it really depends on what is your situation, what are you trying to achieve, and what is considered reasonable by your users. And this is a point that I want to stress. When you are writing your code, good enough is what you are looking for. Does your code run in a reasonable amount of time? Nothing you write in this class should take longer than a minute to process. Absolutely, you should never be waiting longer than a minute for an answer. If you are, stop the code, something's wrong. Does it give the answer in a reasonable amount of time? And is the answer correct? That is all I care about. That is all you need to care about. Do not worry about how messy your code is, other than cleaner code does make it easier to debug. But, if it's a brute force, if you're just brute forcing your way through it, if you are fulfilling the assignment requirements, I do not care. To give you a story from my own time going through getting my master's in computer science, one of our assignments was to write an AI for tic-tac-toe in Java that would play perfectly. The AI could not lose. If it could win, it would win, but it would never, ever lose, which in tic-tac-toe is something that you can guarantee. It's impossible to win if your opponent knows what they're doing. And I had written it, but it was the ugliest, just god-awful chain of if, else statements that you have ever seen. And I was looking at it, I was like, I have got to be missing something. There has got to be a more elegant way of solving this. So I went to the professor and asked him, I was like, Professor, what am I doing? What am I missing? Why is my code so horrible? I was like, wait, stop. Does the AI win? Yes, always. Does it win? Does it take longer than a second to make any of its decisions? No, it's pretty much instantaneous. Then why are you worried? Oh, good point. So yeah, don't worry about making your code run as fast as possible. We'll get to those kinds of efficiencies later on in later courses. For now, I want you to focus on writing functional code. And also, don't get sucked into the language war trap. Now, some of us programmers do like to good-naturedly argue over which language is best. But keep in mind, it's a toolbox. Think of it as an array of hammers. You have jeweler hammers that are measured in ounces, and you have sledgehammers that are measured in pounds. You don't use the sledgehammer on jewelry work because you'll destroy it. You don't use the jeweler's hammer to demolish a wall because it'll take forever if it ever gets done. Use the right tool for the right job. All right. That's enough about languages. Let's talk about runtime and compile time, because that's also something that we've been hearing about quite a bit. So compile time. The moment code is compiled, nothing is running or executing yet. So when you hit the run button in most cases in an IDE, integrated development environment, that's going to trigger a compile event. And what it's going to do is it's going to go through, it's going to look at the source code, make sure all the rules have been followed, and if the rules haven't been followed, it's going to throw an error. This would be called a compile time error. And this would generally be things like, not following this, you forgot a symbol, or you used a symbol in the wrong spot, or you forgot to declare a variable name, or something like that. It'd be kind of the equivalent of writing, you meant to write, the cat is eating dinner, but instead you wrote cat dinner eating is the. Like, yeah, okay, you've got all the right words, but they're not in the right order. You've violated the syntax of the English language. That's kind of what's going on when you get a compile error. Runtime means that the code has been compiled. It's in a form that the computer can understand, and the code is currently being executed. It's actively running. Whether this is an interpreted language, and these two steps happened back to back, or whether it's an executable that you are running sometime after you've compiled it, doesn't matter. The moment the code is executing, that is runtime. If you get an error or a defect at that point, it's called a runtime error. And being able to identify whether something is runtime versus a compile time error helps you identify what you are looking for. And also, I will refer to knowledge as we move into the class. Is this a piece of knowledge that I know at compile time, or is this a piece of knowledge that I know at runtime? For example, a piece of information that I might only know at runtime is, does the user have a controller connected to the computer? I have absolutely no way of knowing or answering that. When I compile the program, I can only know that when the program is running, and I can query the hardware and say, oi, is there a controller here? An example of compile time information is knowing where is the image file for the player icon. That is most definitely something that I should know how to locate at compile time. But mostly we'll be using runtime and compile time for identifying where to look for errors. Speaking of errors, bugs. A bug is the word we use to refer to a defect or error in software. It can also sometimes be a literal bug. So the word bug has existed in engineering lingo since before modern computers. But as the story goes, in one of the older computers, back when they used physical relays that had to physically connect and disconnect from each other, they were running tests on a program, and the tests were coming back bad. Like the validations were not working. So okay, let's pop the hood open and try to figure out what's going on here. And they found a moth that had gotten smashed in one of the relays and was preventing the contact from working correctly. And so they took the moth out, and as they noted, first actual case of bug. So it was the first literal bug ever found in a computer system. And that kind of cemented it for us in the programming industry as to why we call our errors bugs. Very, very amusing story. But the general point of it is that, if you've got an error, you got a defect. Whether it's happening at compile time or runtime, we are going to call that a bug. And the process of finding and getting rid of these bugs is called debugging. which is something that we will take a look at later on in this course. All right, been nattering on for a while. Let's have a little bit of humor. How many programmers does it take to change a light bulb? None. That's clearly an engineering problem. But seriously, how many programmers does it take to get something done? Now, not all of these are programmers, but this is the team from Bethesda that worked on Starfield. Obviously, there was contractors involved and such. There was more than just this that worked on Starfield, but this is the core Bethesda team that worked on Starfield. And while not all of them are programmers, a reasonable chunk of them are programmers. Yeah, software engineering projects involve large groups of people. Like, the day of the solo dev is pretty much dead and gone. It does happen. There is the occasional genius, basically, that is capable of, by themselves, writing amazing software that actually gets used. But that is by far the exception. If you are going to work on any sizable software engineering project, you are going to be working with other people. It's just the way it has to work. So how can we enable that? Well, we enable that by using something called source control. Now, in the past, we used something called SneakerNet to transfer files around. And SneakerNet, for those who might not be familiar with it, is you would take a floppy disk, and don't mock these. These had the incredible, the amazing storage power of 1.44 megabytes. Be in awe of their storage power. Yeah, times have changed, right? I still remember my sheer outrage when the Wing Commander game came out many, many years ago with a speech accessory package. You had to buy separately. I think DLC is ridiculous now. You had to buy the speech pack separate. And I just remember being outraged by the fact that this speech pack, just for the voices, required 20 megabytes of my hard drive. I was like, that's ridiculous. That is almost my entire hard drive. 20 megabytes. Who's going to spend 20 megabytes on speech? Oh, hello, 20 gigabyte downloads. Yeah, times have changed. But to get back on track, literally how SneakerNet works is you copy your information onto a disk, or more likely 4 to 5 disks, and you walk it over to the other person's computer and copy it over. Obviously, you can't do that for a large project. That would be absurd. So the next thing up would be, say, a shared network drive. Like you all have student network drives that you have access to. Or like, say, a Google Drive or a Microsoft OneDrive account. You can specify a folder that you can share with other people. Well, the problem with that is if you don't have the right mechanisms in place, it's too easy to lose work. Say I'm working on a file. I've got a good 30, 40 minutes worth of work that I need to do. So I open up that file and I start working on it. Then somebody else opens up that file and they just have one tiny little bug fix. So I've opened the file. I have that original copy of it. Start working on it. Somebody else then opens the file. Remember, they don't know that I'm working on it. They make their change and save it. I'm still working. I finish my work, save it. I never got that other person's change. I don't know that other person's change exists. So I basically overwrite their work. Their change gets lost. And when it comes time to review the bugs, they're sitting there like, Han Solo in Empire Strikes Back saying, they told me they fixed it. I fixed it, type of thing. Only with less lasers going off. Not going to work, right? It's not going to work. So we use these programs called source control. And there's a lot of different versions of source control. SVN, CVN, Mercurial, Git, which is the one that we're using. A fun story about CVN, or not CVN, CVS. Um, there is a chain of drugstores in the Kansas City area called CVS. So when I first moved to Kansas, like, 20 years ago, and encountered my first CVS, there was a legitimate moment where I was supremely confused as to why there was a brick and mortar store dedicated to source control. I was like, what the heck is going on? And then sanity reasserted itself, and I realized, oh, it's a drugstore. That makes so much more sense. Yeah, programming can get into your head sometimes. You've worked with it for a long time. Like, unironically, I had the serious thought while standing in the Lowe's one time, looking at batteries, looking at a package of 2D batteries, and thinking to myself, well, those are mislabeled. They're clearly 3D batteries. Yeah, it gets to your head sometimes. Back on track. So we have these programs called source control. And how they work, and we'll get more into the detail, is there's something called the repository that has the current version. I go to the repository, I check out a file. That comes with a version number. Somebody else goes to the repository and can check out that same file, and they get a version number. And so we can have multiple people working on the same file at once. We all have our own personal copies. But then the source control also provides conflict resolution. So that person checks in their file, it updates the version number on the source control. I go to check in my file, source control goes, wait a minute, you have an older version number. Let me look at this. Can I auto merge these files together? Or did you guys work on the same part of the program? And if it can auto merge it, it'll auto merge it. But if it can't, it'll kick it back to you saying, yeah, sorry, there's a conflict. You need to fix this. So we have conflict resolution. If you have set up your source control correctly, you have offsite backup. Remember, if you do not have your important files existing in two physically separate locations, your important files do not exist. To give a story, Project Zomboid, which is a fairly popular PC game, actually got their development set back by several years, and this was many, many years ago, because the developers were not using source control, and the current version of the game was on one developer's laptop, and that laptop got stolen. It set them back years in terms of development time. They use source control now. But lots of things can happen. Catastrophic hard drive failure, fires, floods, tornadoes, theft, all sorts of things can happen to cause loss of data on machines. So you want to have them backed up. Source control provides that. It provides the full history of every change ever made. Think of Wikipedia. You go to a Wikipedia article, you can see what was changed on every single revision to a page. Source control provides that for programming. So you can go back and look at every single change that was made to a file throughout the entire lifespan of the project. This also then allows you to backtrack. Let's say that you made some changes and you spent a week or so making changes, and then you realized this was a really dumb idea. Well, you can roll back a week and fix it. Or let's say somebody, not maliciously, just you discover that one of the people on the team introduced a massive security vulnerability to the project. Not maliciously, they just made a mistake. But it was still a pretty bad mistake, and so now you can go back and look, okay, let's look at every single file this person has touched to make sure there's no other similar mistakes. So source control is just vital. If you go into any form of software industry, web development, desktop application development, embedded programming, you're going to be using source control, which is why we'll be using it in this class. All right, let's wrap things up. We've been going on long enough. What about Python? Python is an interpreted language. So when you write your source code and you hit run in Visual Studio Code, you're not going to get an executable. Like I said, there is a way to generate executable files for Python. We're not going down that particular rabbit hole. That's beyond the scope of this course. We're just going to be using it as an interpreted language. So you're going to be writing source code in plain text. And when you run it, it's going to be compiled and just immediately generated. Visual Studio Code is going to be able to provide us with debugging abilities. And like I said before, we will be using Git as our source control method. All right, that's it for this presentation. Make sure you take the quiz. Have a good day.